everyone. Welcome to today's podcast. On today's episode, we are going to talk about rocket and rocket flight. Join me as we journey into the Galaxy Talk Show. My name is Nanekia Jesse, and with me here is Charles. Charles, you're welcome.
Hi everyone, as usual, who is on the table? And guess who I brought today? I brought my friend. Yeah. I think it's too big, but then we're going to talk about him. So this is Galaxy's prototype rocket that probably be launching to suborbital.
Yeah.
So
by 2030.
Yeah. Anyway, thank you very much. I'm grateful to be here, and I brought my baby with me here, so I'm sure a lot will be learned today from my friend here.
Okay. So we would like to know what's the difference between a rocket,
Right.
which is also people call it spacecraft, right? Yes, and an aeroplane.
I think I'll take it from the engine part, because obviously the aerodynamics and everything, the shape and everything looks quite different.
Okay.
But people are asking, so why can't a plane also get into space? You understand? The plane gets to a certain altitude and it has to stop. Why can't it also just fly, get into space and start orbiting? The whole thing is oxygen. Okay, so a plane gets into a certain altitude and it has oxygen sitting there doing nothing. You know, oxygen is for combustion. So the plane engines suck it in and it's free for them. They don't need any form of oxygen from any other place. Whereas my friend here, Mr. Rocket, as it ascends and goes higher and higher and higher, oxygen comes down. Oxygen starts reducing. So this man needs to carry its own oxygen when it's going in an oxidizer.
Okay.
Right. So when it gets into space and it doesn't have oxygen, oxidizer provides the oxygen to still burn and still continue the journey. So that brings about the difference. That's why aeroplanes can't get into space, because they don't have oxidizers. Oxidizers are in spacecrafts, rockets, basically. And then they are able to get into space and then use some of the oxygen to continue their combustion into orbit. So basically it's. And the way and manner it burns, unfortunately, mine is a 2030 model.
Oh, okay.
Okay, so mine doesn't have side boosters. Usually, I mean, it's getting out of date, but most of the companies are beginning to use side boosters. It's like what we can see behind, as there are certain side boosters that carry rocket fuel, solid rocket fuel, right? And they also have the oxidizers, because they also get up into the altitude. So I brought another friend here, my toilet roll, right? So this is how it works, like the side boosters or the solid rocket boosters. They burn from the center, right? So it's like when you put a toilet roll into the dispenser, you take out the center and you unravel it from within.
Okay.
So that's how the side boosters burn. So they start from the center and they start burning. And once they start burning, it doesn't stop. So when you are lighting up a rocket, you have to know that once it's lit up, it's either going to explode, go to its orbit, it won't stop. And you know, it has only one way to come out. So once it starts burning, then it starts pushing down, and then it produces the thrust for it to go up.
Okay.
You understand? And then we have the center ones, you know, and even those ones, when they get up, because they are not too huge, the fuel gets up. Because in every cylindrical rocket, whatever you see there, I mean, whatever you see next to the rocket, it's just full of fuel.
Okay.
It carries nothing. You know, you are burning and producing a huge amount of thrust. So you need a lot of fuel to burn. So whatever you see there, whatever you see in the whole rocket, it's just fuel in there. Fuel at the side, fuel for it to burn. But the difference is the center engines. Those ones are able to throttle up, throttle down, gimbal, because those are the ones going to shape the movement of the rocket.
Okay.
So basically the side boosters are the ones doing the job. They take you up, they come off, and they fall somewhere. They probably disintegrate to get into the atmosphere, or they have a certain part in the ocean where honestly they drop all these things in there. And it's
So talking about the ocean, I remember somewhere last year, a specific country, which I've forgotten, but it happens to be an African country, launched a reusable rocket. And it ended up falling into the ocean. So that means they can take it and then reuse it. I've heard scenarios or issues of rockets also falling in the ocean.
Yeah.
I think even SpaceX did one which fell somewhere close, a reusable rocket. I want to know why they fall around that place. I mean, not where people settle.
People settle. Okay, so obviously in everything we do, there are regulations.
Okay.
You understand? And there are safety precautions that need to take. So in your calculations, when you are trying to get into orbit, it's just like most airports are very close to the sea. Why? Because as soon as you take off and anything happens, then you can fall into the sea without affecting anybody. So you look at most of these rocket launches, they're very close to the ocean, the sea, so it hasn't caused any issue. Now let me clarify. In Africa, we haven't actually launched a rocket yet. We only contract people to.
Yes, so it was a partnership.
A partnership, yeah. So they that's what happened. So it's actually the calculation that your trajectory, where you're going, has nothing there. I remember there was a time SpaceX wanted to launch. Just about a minute to launch. There was a cruise ship that was passing. It wasn't even close to them. But then the trajectory.
Okay.
And the fact that they use reusable rockets, it was going to land. They didn't want to take any precautions. So they had to scrap it. And it's very expensive to scrap a rocket launch because you fill it with fuel. And then when you scrap the launch, you have to get everything off. And it's very expensive. So you can imagine that cruise ship who didn't know and was just strolling by and decided to, just walk through. And that is what caused the thing, the scrapping of the launch. So it is very imperative to make your calculations well. Once you're about to launch, make sure that the whole area, wherever it's going to pass, there's nothing moving there. There's nothing moving there. So that when there's any explosion or when there's any return, it falls straight into the sea and doesn't affect anybody. Sometimes I have issues with the fact that you guys are just dropping things into the ocean like that. But they have a special place where it always ends up at when sometimes they orbit and they deorbit it into, or sometimes it disintegrates.
Okay, so that means a lot of calculation goes into rocket flight.
It's the most complex thing you probably come across. And when we talk of complexity, when you do rocket science, you realize that, look, you've never seen anything complex. Like it just keeps getting complexer, and I say complexest. It just keeps getting tougher and tougher especially when you want to talk about reusable rockets.
Okay.
And apart from SpaceX, they are the only people that can actually get into orbit and come. Blue Origin doesn't get into orbit, do they? They just slide straight up and they get just above the command line. And then they cut off their engines and then they drop straight back and land where they started.
Okay, so is it that those rockets have no mission in space?
Currently, getting into orbit is no joke. It's very tough to get into orbit. She's putting something in orbit. And remember, I love the orbital science. Right? Now, when you shoot something to space from Earth, you want to get into orbit, right? So you are moving from 0 to 18,000 miles per hour, right? Okay. You need to achieve those speeds. And to even achieve those speeds from Earth to orbit, your engines need to be firing at 12 kilometers per second. You understand? 12 kilometers is no joke. And you blink your eye, you are supposed to be at 12 kilometers. Blink your eye next to 24 kilometers. You blink your eye again. So you can imagine the amount of speeds that you need to get into space.
Okay.
Right. So this brings me back to the sweetest part. When a rocket launches, as we can see, when a rocket launches, it just keeps going up, up, up. Then it turns. It rolls.
Just like an aeroplane.
Then turns like that.
Okay.
Why? People ask that question. Why is space not up, 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 up? You just keep going, 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 going. Why are you telling me the rocket is bending?
Yeah, why?
Okay, so when you go up, 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 where are you going? You're just
That's
going.
the question I initially asked.
Exactly.
Yeah.
Where are you going? You're just going. You just go, 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 and then that's all. You're not coming back. So as soon as the rocket lifts off, you hear them saying the vehicle is pitching downrange.
Okay.
It means it is beginning to gimbal its engine. And when we say gimbal, it means they have the engines that are able to tilt, and it's like a steering wheel, but automatically worked on down there. So it begins to tilt. It will obviously go through maximum aerodynamic pressure, which is the maximum stress the vehicle goes through. So it's like you have a thin film like that and you are piercing it with something. So when you pierce it too hard, you can snap the rocket. So atmosphere is a layer. So as you go through the layer, it's beginning to form a lot of forces around it. So it's beginning to get stressed. So if you don't throttle your engines down so that all the stresses will come and pass quietly from you and go, and you still want to maintain a speed, the rocket will disintegrate.
Oh, okay.
So it gets to a place called the maximum aerodynamic pressure. It's called the max Q, where the rocket will throttle down and just allow it to go through the stresses without worrying them. Because already you've disturbed the atmosphere so much. So now it is building a lot of forces around you. It wants to snap you. So I said, okay, I won't let you snap me. I've relaxed. Just leave me and let me get into space. Okay. So then it tilts. And that's where it becomes more important. It's tilting. And Newton sat down and said, okay, so what is orbit? That's where the problem comes in. People ask, so then what is it going to do? Is it getting into orbit? So what is orbit? Why does it need to get into orbit so that we claim that it is in space and then we can have access to whatever you have put in there? Because once you get into space, the fuel is done. The fuel is just supposed to carry you through Earth atmosphere, which is obviously a different set of engines. That's why we have the first stage and the second stage. So the first stage comes off, and the second stage, which is actually going into an area of less pressure, takes over. And obviously that one is smaller, so the fuel is not that much.
Okay.
So they need to maintain those speeds. So you need to talk about this, like, okay, then orbit means you need to fly the spacecraft so fast that because it's close to Earth, Earth is trying to pull it down. It's trying to pull it to fall. But as it's pulling it to fall, Earth is actually also curving away from it. That's why it's a curve. That's why they turn. So the spacecraft is trying to fall, but Earth is also swerving it. Yeah, because it's curving. So that's the science behind the orbit. That's what we call orbit. Because it's pulling you down. You are running at high speeds. It's pulling you. But you are falling, and the Earth keeps turning and turning and turning and turning. Yeah. So as I talk to the flat earthers, I'm like, you both still believe the Earth is flat. Okay. So yeah, that naturally explains what orbit is. Okay. You are trying to move away, Earth is pulling you, and you are falling, but Earth is also curving away from you. That's the nature of orbit. So that explains orbit, right? And secondly, and this is very interesting, and I think a lot of things will be learned here. So this is an example. I have a pen here, right? And I tilt it this way. right? I have a tilt like this way, and I put a ball on it. The ball will roll down, right? Okay. Now, I want to make the ball roll down faster.
Okay.
I don't have the chance because it's stuck here. I can't tilt it like this. It can only be like this. But I really want the ball to get faster. I'm not achieving the speed I want. So what do I do? What is the engineering behind this? And this is nice. From here, it creates something like that.
Okay. Like a slopey something.
A slope like that.
Okay.
A curve like that. So when I put a ball here and another ball on the curve, definitely, you know, the one which is curved will get more acceleration and get faster in there. So if I have a curve that is faster getting down and I turn the curve, right, it becomes this way.
This way, yeah, the opposite.
Opposite.
Okay.
Right. It means if I'm traveling to space, it's even a faster way for me to get there.
The convex.
Yes, the converse way.
Okay.
So that is what we call the brachistochrone problem.
The
Brachistochrone problem.
whoa, the brachistochrone problem.
So it demands a lot of physics, calculations here and there, considering a lot of things, and it's quite complex. But the mind and the sense behind it is because we want to get to space faster because our fuel is burning. We can't just be doing like this. Okay. We have to curve ourselves. So as soon as you curve, you are adding more momentum to you. So you are moving faster. You see how brilliant it is to learn the science all the time. Yeah. So that explains why the rockets, they travel like that. Oh. So it goes like that, and then it turns and it starts its speed hitting 18,000 miles per hour.
Okay.
Right. Because it's actually applying the brachistochrone problem to it. Yeah. So at that point, it just moves faster and then it increases the speed. If it goes like that, the speed might be lesser than it's doing that curved like that. Right. So it's one thing that I've learned today.
The curve around the orbit.
Yes, and they curve into orbit.
Into orbit.
Yes.
And that is called the brachistochrone
problem. Yes.
Okay. Yes. Wow. All right. So we would also like to know, is it that someone sits somewhere and monitors and then regulates the rockets in the sky or space? Right, okay. Or automatically the rocket is actually made in a way that, okay, if I get to this altitude, I know I have to move like this. I know I have to get move along the brachistochrone problem or move by it.
Yeah, so everything is autonomous. Rockets are autonomous.
Okay.
So it is built in a way where as soon as it lifts off, when it gets to maximum aerodynamic pressure, it will throttle down itself because it will realize that it's built in a way that it realizes that I've got to this place. Let me throttle down.
Okay.
It will realize that my fuel is being used up in my first stage. So I need to cut off. You are using a lot of energy moving through our atmosphere. So you wouldn't probably want to use the same amount of energy when you are in space because the space, there's no air resistance. So when you hit space with 18,000 miles per hour, you are definitely using that same speed forever. Okay. When there are one or two issues, they boost you up a bit in space. That's for the satellites and ISS. So sometimes when they realize your orbit is fading or you are deorbiting, they boost you up back into that orbit. But there is no rocket to propel you. So it's the same speed that you run around with. That 18,000 is what you still... So the Earth is pulling you. You are trying to fall. The Earth is running away from you. I want to fall. The Earth says, no. I keep curving and you keep curving and you keep curving like you're falling, but you're curving and curving. So that's orbit.
Okay. So with the rocket, from manufacturing to when it ascends into space and then it moves, what's the name given to the people who actually assemble these rockets?
We're talking about 4,000 technicians coming together to put this thing together.
So they are all technicians
Everyone.
specifically for spacecrafts.
Yes, for rockets. Obviously, you have administrative staff and all that are running around and getting documents ready.
Okay.
But trust me, you need about 2,000 to 4,000 people. It's not a joke getting to orbit. It's some huge, huge work. So you look at the likes of SpaceX, they produce from scratch.
Yes.
Everything comes in metallic and it comes out as rockets. Whereas there are a lot of other rocket companies that will probably tell maybe someone to do this engine for me. This company, you handle this navigation system for me. Okay, you handle the flap system for me. You handle the body. The likes of SpaceX, they like to build their own engines and patent them and tell you, look, we can do our own thing. So it requires a lot.
Okay.
A lot goes into place. Mechanical engineers, electrical system engineers, software engineers, every engineer. I'm sure geodetic even comes inside.
Yeah, of course, it's needed.
Yeah.
And then we would like to find out. I think a question just came in. What kind of fuel is used? Is it diesel? Is it petrol? Or is it a special kind of fuel?
Right. Okay. It's a very, very important question, and people usually ask these questions. So in the side boosters, we have hydrogen and oxygen.
Okay.
When you hear hydrogen and oxygen, what comes into mind? H2O.
Yeah, water.
H2O, water stuff. So hydrogen is very reactive, very exothermic. Very, very exothermic. So they run it through they actually liquefy it. It's just like you go and buy your gas. Okay. When you shake it, it's like water is inside.
Yeah.
When you are using it, it's gas.
Yeah.
So that's why you call it LPG, liquefied petroleum gas. So they liquefy the hydrogen, they liquefy the oxygen, and then they run the tubes, and then poof. So sometimes you hear the launches, SpaceX, LOX load complete. That's liquid oxygen.
Okay.
That is put into it to also fly to help with the combustion and everything, but it's actually hydrogen and oxygen that is mixed, and then the end product is water.
Yeah. All right. Wow. Wow. Rockets are actually an interesting topic to delve in, and as a space enthusiast, someone who wants to enter into the field, I believe this is actually giving you an overview of how rockets operate.
And also, I think I explained that the liquefied part as well. So those who go and buy gas and are still wondering, is it that I shake my gas, I feel water? But it's gas that comes out.
It's heavy. The water in it
is heavy. Yeah, it just means it's been liquefied. But then when it comes out as gas. Yeah, so that's the same principle that's used in the rockets.
All right. Okay. So thank you all for joining us, and stay tuned for more exciting podcasts coming up. And with all your questions, follow us on Galaxy Aerospace Ghana on all our social media platforms. You can ask your questions through our media platforms and also through the number that will be provided over there. Let us hear from you. Let us be interactive. Till we meet again. Bye.